This video is on adding and subtracting radicals, and I want to remind you of something that you should have already learned when you were adding and subtracting polynomials, and that is the fact that you can only combine terms if they are like terms. So for example here, 3x and 5x are what we call like terms. They have the exact same variable component or part of the term. So if you have 3 x's and someone gives you 5 more x's, you can combine those and now you have 8 x's. We also learned that you cannot combine terms if they are not like terms. So for example, 3x plus 5y, we can't do anything more to that to simplify it. If you got the answer 3x plus 5y, your answer is just 3x plus 5y because you cannot combine those. Radicals are very similar. If you have 2 square roots of 3 and someone gives you 5 more square roots of 3, you can add those together. Those are considered to be like terms. It's square roots of 3 that we're combining. How many of them do we now have? We would now have 7 square roots of 3. So for radicals to be like terms, they have to have the same exact thing under the radical. And if they do, then they're like terms and you can add or subtract them. However, if you have different numbers or variables under the radical, you will not be able to do anything more to those as far as combining them. 2 square roots of 3 plus 4 square roots of 2 would just stay as it is. So, I'll go through a few of these. If you have 6 square roots of 11 and you take away 2 square roots of 11, you would now have 4 square roots of 11. Or if you have the square root of 3 plus the square root of 3. In a case like this, this has an understood 1 in front of it. You have 1 square root of 3. And this has a 1 in front of it. So you have plus another square root of 3. And that will give you 2 square roots of 3. Alright, if you have 5 square roots of 6 and you take away 8 square roots of 6, then you're going to have negative 3 square roots of 6. And it doesn't matter how complicated whatever's under the radical gets, you still would do the problem the same way. In this particular example, we have cube roots of AB. But all of the terms have the exact same radical, and what's under the radical. Cube roots of AB, cube roots of AB, cube roots of AB. So if you have negative 2 cube roots of AB plus 7 cube roots of AB, now you have positive 5 cube roots of AB minus, this has an understood 1, so minus 1 cube root of AB would give you 4 cube roots of AB. Okay, one more and then we'll go on to something a little more complicated. Let's do one with fractions in it. If you have 1/4 square root of 3y minus 3/2 square root of 3y. Okay, these are like terms. They have the same thing under the radical in each problem, which is square root of 3y, square root of 3y. We can combine them, so we're going to subtract these fractions that are in the front. When we subtract fractions, we've got to get a common denominator. So my common denominator for 4 and 2 is going to be 4. Up top, I've already got a fraction with a denominator of 4, so I don't have to make any changes to that. Here, I'm going to multiply the top and bottom by 2 because that's what I would have had to multiply 2 by to get 4. So whatever you do to the bottom of the fraction, you have to do the same thing to the top. So we end up with 1/4 minus 6/4, and that's going to be negative 5/4. So I'm going to come back over here to my problem, and my final answer is going to be negative 5/4 square root of 3y. Okay, so I already said if we don't have the same number under the square root or the cube root or whatever radical you happen to have in your problem, then you do not have like terms. So this is a case where we do not have like terms. However, if either one of these radicals will simplify, or both will simplify, we need to simplify them if possible, and then re-examine the problem to see if we can combine anything, because sometimes after you simplify you may end up with like terms. Now 2 will not simplify, but 8 will, and there are 2 ways that you can think about simplifying the square root of 8. You can break 8 down until you get all prime factors. Okay, so the square root of 8 is 2 times 2 times 2. And then anything you have a pair of tells you that there was a perfect square in that 8, and it was 4, because I have a 2 times 2 is 4. That's what's telling us that this can be simplified. Is if there's a perfect square that goes evenly into 8, then it can be simplified. And by breaking it all the way down, anything that you have a pair of tells you that's what the perfect square was in there. So this had a 4 in there. And so if you have a pair of 2's, you're going to bring 1 2 out. This one's going to be left underneath the square root. Now you can also, instead of breaking it all the way down, you can say what perfect square goes evenly into 8, and you want to pick the biggest one that you can think of that goes evenly into 8, and it would be 4. And you can break it down saying how many times will 4 go into 8? It goes 2 times. So I'm breaking down my 8 to 4 times 2. The reason, because 4 is a perfect square. I can take the square root of 4. The square root of 4 is 2. I cannot take the square root of 2 and it come out to be a nice whole number, because 2 is not a perfect square, so I leave it under the radical. So either way, you get 2 square roots of 2. But you have to remember you have this 3 out here. So you have 3 times 2 square roots of 2 for this first one, and that's going to be, I haven't really left myself much room here, that's going to be 6 square roots of 2 plus the square root of 2. And that's got an understood 1 in front of it. And so when I combine those, I'm going to end up with the final answer of 7 square roots of 2. So this is just me reviewing how to simplify a radical. You want to simplify the square root of 8. Whatever you get, whatever comes here to the outside has to be multiplied by the number that was already outside the square root of 8. So this 2 that came out gets multiplied by the 3. That gives us 6 square roots of 2 plus the other square root of 2 that we had, for a total of 7 square roots of 2. All right, let's try another one like that. Square root of 50 plus square root of 72. Now if you want to break those numbers all the way down to prime factors, you can, or you might see that the perfect square 25 goes into 50, and it goes 2 times. And so I can break 50 down to 25 times 2. The square root of 25 is 5, and I would leave the 2 underneath because it's not a perfect square. For 72, I just so happen to know that 36 goes into 72 twice. 36 is the largest perfect square that would go into 72, and so that ends up being 6 square roots of 2. Square root of 36 is 6. The 2 is not a perfect square, so it stays underneath the radical. Then we can combine those and we get 11 square roots of 2. Now if you didn't know that 36 would go into 72, remember that you can break 72 down until you get to all prime number factors of 72. And then you can list your prime factors. 72 is 2 times 2 times 2 times 3 times 3. Okay, that's what was at the end of all my branches in my factor tree. Anything we have a pair of indicates that there's a perfect square in there. So there's a 4 in there and there's a 9 in there, okay? Which means a 2 is going to come to the outside and a 3 is going to come to the outside, and we have a 2 underneath. So we end up with 6 square roots of 2. And you see that's what we got here. So I just happen to know that 36 went into 72 twice. But if you didn't know that off the top of your head, you can always break 72 down until you get prime factors and do it that way. All right, let's try another one. Square root of 45 plus square root of 80. So again, if you know your perfect squares and you can figure out which perfect square is the largest one that will go into either of these, then you can simplify them that way. So for 45, I know 9 is a perfect square that will go into 45. So I can break 45 down to 9 times 5. Square root of 9 is 3. So that simplifies to 3 square roots of 5. For 80, I believe 16 is the largest perfect square that will go into 80, and it goes 5 times. Again, if you didn't know that, you can take 80, you can do your factor tree, break it all the way down. Square root of 16 is 4. 4 square roots of 5. These are now like terms, and I can combine them and get 7 square roots of 5. Okay, let's do one with some variables in it. If I have 8 square root of x cubed y squared minus 3y square root of x cubed. You can see here that these are not the same right now. So we're going to attempt to simplify those and then see what we get and see if it can be combined. Alright, so again, for square roots, we're looking for perfect squares underneath the radical. If you want to, you can write these out in the expanded form. We're looking for pairs, because pairs indicate perfect squares. So I have a pair of x's, that's like an x squared, which is a perfect square I can take the square root of. I have a pair of y's, which is y squared, so that's a perfect square. So I'm going to be able to bring out an x and a y here. That's going to leave one x underneath the radical. Then here, got a pair of x's, that's an x squared, so the square root of x squared is x. When I bring that out, I'm going to stick it right here in the middle because I like mine to be in alphabetical order. And I'll have one x left underneath the radical. And as you can see, now that I've simplified, I've got like terms that can be combined. This in the front, these are also alike, so 8xy minus 3xy is 5xy, square roots of x. Okay, now I think I can fit one more on here. Square root of 50x squared minus 3 square roots of 8. Okay, again, if you wanted to break it all the way down, you could. If you want to say you know your perfect square that goes into 50 is 25. X squared is also a perfect square. So I've got a perfect square here and a perfect square here. The square root of 25 is 5. The square root of x squared is x, leaving a 2 under the radical. Square root of 8, I know 8 breaks down to 2 times 2 times 2, so there's a 4 right there. The square root of 4 is 2, so a 2 is going to come to the outside. Get multiplied by that 3, so I'm going to end up with minus 6 square roots of 2. Now on this one you see that the square roots of 2, that part's the same, but the part in front these are not like terms. We can still combine these into one expression like this. We can put 5x minus 6 together in front of the square root of 2. But don't try to subtract that and tell me it's like negative 1x or something like that. You cannot combine those. Those are not like terms. But we can write this all as one expression on the square root of 2. Okay, just a couple more and then we'll wrap this up. Cube roots, I do want to show you that cube roots and even fourth roots and fifth roots would be done pretty much the same way. They would have to have the same number under the radical to be able to add or subtract. These do not, so we're going to attempt to simplify them first. When you're simplifying cube roots, you're looking for a perfect cube that goes evenly into this number. So these might be a little tougher. If you want to break them all the way down, that's an option as well. If we break them down to prime factors, we see that 81 is 3 times 3 times 3 times 3, and 24 is 2 times 2 times 2 times 3. And when we're simplifying cube roots, we want to find perfect cubes in here, which means we would need 3 things that are the same. 3 times 3 times 3 is 3 cubed, or 27, and that's a perfect cube. 2 times 2 times 2 is 2 cubed, or 8, and that's a perfect cube. So because we found 3 of these in here, and we know that's 27, the cube root of 27 is 3. So a 3 is going to come to the outside. This 3 is left under the radical. Okay, here, 2 times 2 times 2 is 8. The cube root of 8 is 2. So a 2 comes to the outside, and a 3 is left under the radical. 3 cube roots of 3 minus 2 cube roots of 3 is 1 cube root of 3. Do you have to put the 1 there? No, you don't. You can just put this, and there would be an understood 1 there. All right, last problem. This is kind of just a more advanced one, or it looks a little scary, but we're going to do it just like we've been doing all the others. Okay, lots of things going on here. We're back to square roots, so we're looking for perfect squares under the radical that would allow us to simplify it. We can break these numbers all the way down. We can, if we want to do it that way, we can look for the highest perfect square that goes into each of these. I am going to do that. So I know 25 goes into 50. And when you do these problems enough times, you'll start to know some of these off the top of your head like I do. All right. If we divide 50 by 25, that leaves 2. X squared is a perfect square, so I'm going to leave it alone just like it is. Y to the 5th is not a perfect square, but any variable to an even power is a perfect square. So the highest even power that's less than 5 is 4. So I'm going to break down that y to the 5th to y to the 4th times y. Now I have a perfect square here, a perfect square here, a perfect square here. All right, if I take the square root of all those, I have 5xy squared. And left underneath my radical, I have 2y. All right, let's try this next one. It's got a 13y on the outside. The 2 cannot be broken down. X squared is a perfect square, so I'm going to leave it alone. Y cubed is not a perfect square, but the highest even power of y, that's less than y cubed is y squared, which would leave one y left over. All right, so I have a perfect square here and here. All right, so an x is going to come out and a y is going to come out. So when that happens, I'm going to have negative 13x. I already had one y out here. When I bring another y out, I'm going to have y squared. And left underneath, I'm going to have 2y. And now I'm going to look at this last one. I have plus xy. 98. I know 49 goes into 98 2 times. 49 is a perfect square. Again, y cubed is not a perfect square, but the highest even power that's less than 3 is 2. So y squared times y gives us y cubed. This is a perfect square. This is a perfect square. Square root of 49 is 7, so I'm going to have 7 out here. I'm going to have x. I already have one y, and the square root of y squared is another y. And then 2y left underneath. All right, when I look, I see that these are all alike. I see that these are all alike, so we can combine. 5xy squared minus 13xy squared is negative 8xy squared. Plus 7xy squared would be negative 1xy squared. Square roots of 2y.